Jai Hind everyone. This is Dr. Naresh Kumar from Ajay Kumar Garg Engineering College, Ghaziabad. Welcome to the class of Optical Communication. In this video lecture, we will discuss the effect of temperature on the avalanche gain of the photodiode. We will also compare the various type of photodetectors considering various parameters, and finally we will calculate the signal to noise ratio for the optical receiver or in the case of photodetector. So the main contents for today's lecture will be, we will study in detail what will be the effect of temperature on the avalanche gain, and next will be the comparison of various type of photodetectors considering various type of materials or fabrication. Next is, we will also calculate the different type of noises available in the case of photodetector or receiver, or what are the sources of noises or errors in the case of photodetector or optical receiver. And finally we will calculate the signal to noise ratio for the photodetector or optical receiver. So today's first topic is effect of temperature on the avalanche gain. Basically we have studied that in the optical receiver the first component available is the photodiode, and examples of photodiode can be either PIN photodiode or it can be APD. And we have studied that out of these two photodiodes, PIN is known as the photodiode without internal gain, whereas this APD, that is avalanche photodiode, is known as the photodiode with internal gain. Okay, this internal gain is denoted by the factor M. For example, in the case of PIN, whenever the light is incidented over the photodiode, if this is the input power, at the output we will get the photocurrent IP because of photocarriers. So in the case of PIN we will get the IP, whereas in the case of APD we will get is IM, that is M multiplied by the IP. That means M is the internal gain that we are getting additionally in the case of APD, avalanche photodiode. This additional internal gain is because of the secondary generation of photocarriers, because of impact ionization initially, and after that because of the avalanche effect. Because whenever we apply a comparatively higher reverse bias voltage in the case of APD, the photocarriers generated move with a great velocity and gain sufficient energy and collide with the material particles so that they can generate further photocarriers. So in the case of APD, because of secondary carrier generation, electron hole pair keep on increasing, and because of these additional electron hole pair, because of avalanche effect or impact ionization, we get this additional factor M known as the internal gain. Now in this topic we will study what will be the impact of temperature gain on the avalanche gain. What is the impact of temperature? Basically, with the change in temperature, this internal gain M should remain constant. But in the case of semiconductor we have seen that whenever there is slight increase in the case of temperature, especially when we are operating near the threshold, then the performance can change drastically even when due to slight change in the temperature. Here we have seen that as there is change in the temperature, the gain of the system gets changed, and during the working of APD diode we have also seen that the performance of APD is also changed according to the applied reverse bias voltage. Okay, so this M also depends upon temperature. So basically we can see that the avalanche gain in the case of APD diode depends upon the temperature as well as on the applied reverse bias voltage. So, to nullify the impact of this change in temperature over the avalanche gain, we can change the reverse bias voltage accordingly, so that the performance of the system or gain of the system remains constant irrespective of temperature conditions. That we will see in this topic. So, this is the relation of temperature dependence of internal gain M over the voltages as well as the N constant. These are the characteristics showing the impact over the current gain. Current gain is M with respect to voltage as a function of temperature. So, from this characteristics graph for the APD diode, we can see that the current gain depends upon the applied reverse bias voltage and it also depends upon temperature conditions. So, to achieve a constant performance with respect to temperature, what we will do is we will use a compensating network or compensating circuit. A compensating circuit will be used that will adjust the reverse bias voltage to nullify the effect of change in temperature. So, due to change in temperature, whenever there is a change in temperature, increase or decrease, then the gain will also may increase or decrease. So, gain can be controlled by controlling the voltage also. So, this compensating circuit will adjust this applied reverse bias voltage either increase or decrease, so that the effect over the gain is nullified for the case of change in the temperature. So, from this characteristic graph we can see that the performance of the photodiode APD, or we can say that the current gain, internal gain M, depends upon voltage as well as over the temperature. So, effect of change in the temperature over the avalanche gain is nullified by using a compensating circuit by adjusting the applied reverse bias voltage accordingly. So, next topic is comparison of photodetectors. Basically, we have seen that the photodiode or photodetector can be either PIN or APD. Now, these two type of photodiodes, for example PIN, can be made up of using various materials. Semiconductor materials are used for making these PIN or APD. So, let us say first of all we have PIN photodiode. This PIN photodiode may be made up of silicon material, it can be made up of germanium, it can be made up of indium gallium arsenide. So, basically in the first comparison table we are talking about the performance of PIN photodiode based upon various materials silicon, germanium and indium gallium arsenide. Now, we will compare the performance of the photodiode, PIN photodiode made up of silicon, made up of germanium and indium gallium arsenide based upon these performance parameters. Okay. So, first comparison parameter is wavelength range. So, the operating wavelength. So, if we have to operate in the short wavelength region, then a PIN photodiode made up of silicon performs better. Now, we can see that if we have to operate in the longer wavelength region, then we have to prefer either the germanium or PIN photodiode made up of indium gallium arsenide. So in this way we have to compare the performance of PIN photodiode made up of silicon, germanium and indium gallium arsenide based upon these parameters. Another important parameter is, let's say for example, dark current. Dark current is basically the small amount of negligible current may be available at the output of photodiode even when there is no optical power incidented over the photodiode. That means without the presence of light, there may be some negligible amount of current available at the photodiode output. This is basically a noise, and this noise is known as the dark current. So dark current should be minimum as low as possible. So next parameter is dark current. So dark current should be minimum or as low as possible. So now we will see that the dark current is, in this case, silicon is 1 to 10 nanoampere, germanium it is 50 to 500, in the case of indium gallium arsenide it is 0.5 to 2. So we can see that based upon dark current parameter, the PIN photodiode made using indium gallium arsenide performs the best. So in this way we can do some comparison. Another is, let's say for example, rise time. Rise time tells us about the speed or response time of the system. So rise time should be low, that is speed of the system should be fast. Speed of the system should be fast or high. So a photodiode having the minimum value for the rise current perform the better. So rise time is basically time taken for the signal to reach from, let's say 10 to 20% to, let's say 90 to 80%. So this time is called as the rise time, and reverse for this, that will be fall time. Okay, so rise time should be minimum. So we can see that rise time here is 0.5 to 1, here is 0.1 to 0.5, and again here is 0.05 to this one. So we can see that the rise time is minimum in the case of indium gallium arsenide based PIN photodiode. In another, we can also compare these photodiodes based upon another parameter such as modulation bandwidth. So modulation bandwidth is maximum in the case of indium gallium arsenide. Again, bias voltage, reverse bias voltage applied requirement 5.55. So again this one have minimum value. So another parameter that can be taken is responsivity. Responsivity is basically R, that is what we are getting at the output, IP, what we are applying at the input is in P. So this is the responsivity of the photodiode, and this IP should be maximum even when small amount of power is applied. So responsivity should be high. So high responsivity is desired from a photodiode or photodetector. So responsivity, we can see that here is 0.4 to 0.6, 0.4 to 0.5, it is 0.95. So we can see that here it is performing the better. So based upon this comparison, we can conclude that if we have to operate at short wavelength region, then silicon based PIN photodiode performs better, and in all other cases the indium gallium arsenide based PIN photodiode performs better as compared to PIN photodiode made up of silicon or germanium. As we have done or studied this type of comparison for the PIN photodiode, in the similar way we can compare the performance of APD photodiode also. So continuing from the previous slide, in this case we are showing the comparison of APD photodiode that is made up of silicon, germanium and indium gallium arsenide, and again we will compare the performance of these photodiodes based upon various parameters like wavelength range, avalanche gain, dark current, rise time, gain bandwidth and bias voltage. For example, again in the case of bias voltage wavelength region, for short wavelength and for long wavelength region. Avalanche gain is maximum in the case of silicon, so it is better. Based upon dark current, it should be minimum, so minimum is in the case of silicon. Again, rise time is again minimum in this case also, but it is minimum. Gain bandwidth, so gain bandwidth is maximum in the case of silicon, so silicon is preferred. Bias voltage requirement is minimum in the case of indium gallium arsenide. So in this way we can compare the APD photodiode performance that is made up of silicon, germanium and indium gallium arsenide using these performance parameters. Now the optical communication is highly wavelength dependent, because we have seen that the attenuation is maximum at shorter wavelength region and it is minimum at longer wavelength region, let's say window 3 at around 1550 nanometer. So optical communication is highly wavelength dependent. So based upon operating wavelength region, we can decide that for short distance applications, and if we are operating around 850 nanometer, that is window 1, then the silicon based devices, that is silicon based photodiode gives the best performance. In the similar way, if we have to operate in the longer wavelength region, that is around window 2 and around window 3, then we have indium gallium arsenide based photodiode that gives the best performance. So this is the conclusion for this topic. Now last topic in this today's lecture will be photodetector receiver and the equivalent noise circuit. So basically we are calculating the SNR in the case of photodiode or receiver. Okay, so for calculating the SNR, we have drawn this is the simple photodetector receiver. In this case we have photodiode where the light is incidented over the photodiode, and just after the photodiode we use a amplifier. This amplifier is basically known as the front end amplifier. Now the question arises, why we require the amplifier here? Basically the signal reaching to the photodiode is generally a weak signal because it is reaching after passing through the fiber, and in the fiber we know that there is attenuation because of absorption, scattering, fiber bending or any other mechanisms. So there is loss, that's why the signal is very weak, and if the signal applied or power applied here is very weak, then the corresponding electrical signal or photocurrent obtained will also be very weak. So to amplify or to improve the strength, we use an amplifier just after the photodiode, and this amplifier is known as the front end amplifier. Now if we draw the equivalent circuit for this receiver, we will see that in the equivalent circuit this is the photodiode, and corresponding to the photodiode and the amplifier we have a number of resistors here and a number of capacitors here. Okay, for example we have junction capacitance, load resistance amplifier resistance, amplifier capacitance, and we have a resistor in the series to control the flow of current. So we have a number of resistive components combinedly together denoted by RT, and a number of capacitive components combinedly denoted by the CT. Now, what are the sources of noise available in the photodiode or photodetector, or we can say that optical receiver, because the photodiode is the first component available in the optical receiver. So, sources of noise available in the photodiode will also be considered as sources of noise or error in the case of receiver. And in the receiver, we additionally will also have the amplifier effect also. So, the main sources of noise will be, during the photo detection process, the noises available are quantum noise, because the arrival of photons over the photodiode and collection of electron hole pair after being generated through the avalanche effect, or in the case of PIN photodiode, the electron hole pair are collected. So, that process follows a Poisson process or Poisson equation, or that noise is known as the quantum noise. Quantum noise also known as the short noise. Some noise also present, that is dark current. We have studied, even when the light is not incidented, small amount of photocurrent may be available at the output side. This is known as the dark current, that is current without the presence of light over the photodetector. It should be minimum. Then we can also have background noise or beat noise. We can also have avalanche gain in the case of APD. So, fluctuation in this gain can also be there. So, gain fluctuation also appears as a noise. Now, we can also have amplifier part. In the amplifier, the main dominating part is the thermal noise, due to thermal molecular vibrations or movement of the particles or molecules in the resistive components. This thermal noise is mainly present because of the resistive components. We know that this we have thermal noise is equal to 4k T BE by RL. This is how we calculate the thermal noise, or this thermal noise is also known as the Johnson noise. Okay. Then we can also have some small amount of leakage current or surface leakage current. Noise power. Basically, the main aim here is to calculate the noise power corresponding to all of these noise sources or sources of error available in the optical receiver. So, now SNR calculation, we know that signal to noise ratio, then we have signal power corresponding to useful signal. And we know that the useful signal in the case of photodiode is, at the output we get is photocurrent IP. So, the signal power corresponding to photocurrent is corresponding to signal. Then we have to calculate the noise power. So, noise power in the case of receiver, we know that receiver has two parts. One is photodiode, another part is amplifier, that we have seen in the previous circuit. So, the power will be corresponding to the noise available in the photodetector and power corresponding to noise in the case of amplifier. That is, we have to consider the combined noise power for the noises available in noises or source of error available in the case of the photodiode and the receiver. So, ideally the SNR should be infinite, or practically it should be as high as possible. So, first of all we have to calculate the signal power corresponding to photocurrent. So, photocurrent is IP. So, the power corresponding to the photocurrent or useful signal is given by this. We have the power given by the mean square of the signal current. So, this is the power corresponding to PIN photodiode power signal. This is the power signal corresponding to APD. We know that in the case of APD, we have the additional factor of M, internal gain, where this M is the internal gain. Okay. Then basically we have to calculate the noise power. Okay. So noise power will be calculated by considering all the type of noises or errors that we have discussed previously. So noise power will be calculated by the sum of short noise, dark current and surface leakage current, etc. So this one is given. So here we have only the short noise is considered as the dominating, and these two may be neglected. Dark current or surface leakage current may be neglected. Another, basically these are the noises available in the case of photodiode. Now the noise available in the case of amplifier, it is the Johnson noise or the thermal noise. Okay. So the signal to noise ratio will be calculated. Power corresponding to useful signal photocurrent, that is corresponding to IP, and noise power calculated corresponding to the all the noises which are available in the case of photodiode and in the case of the amplifier. And then we calculate the corresponding signal to noise ratio by considering only the thermal noise and corresponding to the short noise. Okay. So in this way we can calculate the signal to noise ratio for the photodiode or for the optical receiver. So that's all for this lecture. Thank you everyone. Jai Hind.